Hello everyone, I am Liang Huachi, an embedded engineer from the System Development Department. Today I will introduce the routine of an internal sensor in APM32F4. First let's learn the temperature sensor and its application in our life. The temperature sensor is a device that measures the cold and hot degree of an object, and provides temperature measurements in a readable form through electrical signals. After detecting the temperature of the tested object, the temperature sensor will convert itself into an electrical signal to facilitate subsequent calculation. The temperature sensor can be classified into two categories. One is contact-type temperature sensor. The other is non-contact temperature sensor. The contact-type temperature sensors require physical contact with the tested object. They monitor temperature change through conduction, and can be used to detect the temperature of solids, liquids, and gases within a very wide temperature range. The non-contact temperature sensors do not require contact with the measured media. However, the temperature changes generated by thermal radiation or convection of the tested media will be transmitted to the temperature sensor, and can be calculated according to the calculation formula. This type of sensor is mainly an infrared temperature sensor. Its main feature is that it can measure the temperature of moving objects and objects with small heat capacity. In our life, the contact-type temperature sensors are mainly used for thermistors, thermocouples and thermostats. The thermistor is a kind of sensor, and its resistance value changes with temperature. According to the temperature coefficient, the thermistor can be divided into positive temperature coefficient thermistor and negative temperature coefficient thermistor. Then, the resistance value of the positive temperature coefficient thermistor will increase with the increase of temperature, while the resistance value of the negative temperature coefficient thermistor will decrease as the temperature rises. Most applications in our life are negative temperature coefficient thermistor. Then the following thermocouple is a commonly used temperature measuring element in temperature measuring instruments, and it can directly measure temperature and convert the temperature signal into the electric signal. The electric signal is converted into the temperature of the measured objects through electrical instruments. The thermocouples are usually used together with display instruments, recording instruments, and motor regulators. The picture on the right is their application map. The third type is the thermostat. The thermostat is composed of two bimetallic strips of different metals. Its working principle is that these two metal strips stick together, and when the weather is cold, the contact will close, and current will pass through. When the current passes through, it will heat. One metal will expand and bend compared with the other metal, resulting in an elastic deformation. When the elastic deformation of one metal is larger than that of the other metal, it will bend upwards, the contact will break, and the current will break. This circuit will be disconnected, and then it will produce a temperature control effect. The following is a non-contact temperature sensor. Its application is infrared temperature sensor. Its main principle is that after the sensitive element of the detector absorbs radiant energy, the temperature will rise, and some relevant physical parameters will change. By measuring the changes of these physical parameters, we can determine the infrared radiant energy absorbed by the detector, and infer the temperature of the measured object. It is composed of an infrared transmitter and an infrared receiver. Once the infrared emitter generates emission, it will reach the surface of the object and then rebound. It will reflect back some infrared parameters, as we can measure some of its parameters according to the calculation formula. According to some physical quantities and infrared radiant energy received by the infrared receiver, we can calculate the temperature of the object. If you are interested in it, you can search for more information on the internet and make further study. We only introduce some applications of the temperature sensor. The second chapter introduces the temperature sensors inside our chip. Then let's take a look at the conversion principle and process. There is a control bit in the ADC, CCT or L register, a bit of TSensor, which can control the enable state of the internal sensor. The internal sensor monitors the temperature of the CPU in real time and outputs an analog quantity, the voltage value of sensor. That is to say, after the temperature sensor collects the temperature of the CPU, it will output a voltage signal of sensor. Then, the V sensor can be collected through the ADC 16 channel. Then we can convert it into our data volume, and through conversion by ADC, a voltage value of this sensor can be converted into our data volume, which is convenient for subsequent calculation. Finally, we can perform some related calculations with this data and according to a formula, and deduce the temperature value of the CPU. This is a conversion process. In the calculation formula mentioned above, T and V sensor are the temperature of the temperature sensor, the temperature measured, and the voltage output by it. V25 and 25 below are reference values. That is to say, at 25 degrees Celsius, the temperature sensor outputs a V25 voltage value. A Vg slope is the average slope of the temperature and sensor curve. Since the industrial characteristics of each chip are not exactly the same, the data measured by each chip is different. We obtain a relatively accurate slope based on a large amount of data, and there is also a basic value. Finally, we obtain this formula. This is a reference value, and the corresponding output voltage at 28 degrees Celsius is 0.778 V. And the slope is 2.4 millivolts per degree Celsius. Subsequently, we will use this formula to make a calculation. The following is a setting for the application routine. The programming idea is to configure DMA peripherals, use DMA for transmission, then configure IDC1 and select 16 channels, and configure the sampling time to 480 cycles. The sampling time must be greater than 17.1 microseconds. Then set the control bit of TSensor to enable the internal temperature sensor, then enable DMA mode, and enable IDC to activate the IDC changes. Then read the conversion result and calculate the corresponding temperature value according to the formula. Finally, print out corresponding information through the serial port. Serial port line is used in hardware design. On a mini board of APM32F4xx, connect one TX and RX of serial port 1 to the computer to make it convenient for us to observe data. In the design of the software, configure the serial port, DMA and IDC, and then write the logical subject code of this function. Next, we will focus on analyzing how to configure IDC. This block is a general configuration of IDC, and the resolution of the IDC is 12 bits. The data is right-aligned, not needing continuous scanning, and continuous conversion is required. This is edge-triggered, and it is not necessary. This is a general configuration. Then the following is to configure the work clock of IDC. Because the maximum work clock of IDC is 36 MHz, we need to divide it evenly, and the work clock of IDC finally obtained is 21 MHz. Then select 16 channels and configure the sampling period to 480 cycles. Based on the work clock and sampling period, we can calculate the sampling time T, which is approximately 23 microseconds, greater than 17.1 microseconds. Therefore, we can accurately sample the voltage value output by the internal temperature sensor. The next step is to set the TSensor bit to enable the internal temperature sensor. Finally, enable DMA, enable IDC1, and then start the conversion of IDC1, and the IDC peripherals have been configured. Then let's take a look at the logical subject. The logical subject is simple, and it is to calculate the voltage and temperature values according to some formulas. The first step is to obtain a data type data transmitted from DMA, and then calculate the output voltage of the internal sensor according to this formula. Since our ADC configuration is 12 bits, here it is the 12th power of 2, and then obtain 3.3 V. Then we can calculate the output voltage of the internal temperature sensor. The next step is to calculate the voltage during the temperature sensor conversion according to this formula. The collected voltage is the voltage of the CPU. The final step is to print out the corresponding information through the serial port, to facilitate observation. The last is practical demonstration of the application routine. Our routine is built in IDE development environment of Kiel MDK. We select the APM32F4xx chip. According to the programming idea we just mentioned, configure the serial port, DMA, and ADC, write the logical subject code of the function and then compile. When there is no compiling error or warning, download to our mini board. Then print out that information through Serial Assistant to facilitate observation. This is a data value converted by the ADC. Then convert it into the output voltage of the internal temperature sensor, and then calculate the temperature value of the CPU collected by the internal temperature sensor according to the formula, which is relatively simple. Okay, finally let's review and summarize. The first step is to learn the conversion principle and process, to make it easy for us to write logical code in the future. The second step is to configure relevant peripherals. We should focus on the collection of IDC, namely its sampling time. The sampling time of IDC cannot be less than the calculated conversion time of the internal sensor, namely 17.1 microseconds. Then according to the conversion principle and the formula, infer an output voltage of the internal sensor and the temperature value collected. Okay, that's all for today. Thank you.